Thank you very much. Hello, everyone. Welcome to my talk, The Journey to 1 Million. I'm Samuel, and today we're going to be talking about how to make Ruby more scalable. So let us consider how to improve Ruby. What would we want Ruby to look like in 10 years? Syntax? Do we want to change it? Is it feasible to remove existing syntax if we don't like it? Should we add new syntax? Improvements to syntax can make programming easier. Sometimes the changes feel superficial, or sometimes they cause confusion. It can take a long time until we can use syntax in new gems if we want to support older versions of Ruby. But it's a really important area which makes Ruby the language we all love. What about performance? Ruby generally is only 10 to 100 times slower than native C. But how about parallelism and concurrency? We are facing a future with a wide range of possibilities. C Ruby may implement guilds, Truffle Ruby may manage to avoid the GVL, so threads work really well, so does JRuby, and the JIT is improving. There are many places where Ruby collectively is moving forward, but what are we aiming for? What path do we want to focus on, and where can we get the most benefit? How about the libraries we use every day? Rails, RSpec, Rack, Bundler, and others are critical to the workflow of many businesses. How should they evolve to make our life as developers easier and more productive? As Ruby grows into many different implementations, cross-interpreter support is becoming more and more important. Rather than implementing features in the core of Ruby, it's much more gentle to make gems that work with all implementations. Ruby's standard library is in the process of being gemified. More and more libraries will be turned into Ruby gems, which can be updated independently from Ruby. It's really great to see Ruby embracing this diversity, and I think it's very important. We have a pretty good idea of what Ruby 3.0 will look like, but what does Ruby 4.0 look like? It's definitely got to be faster than C. I also hope we can add a new artificial intelligence operator, which anticipates what you would want your code to do before you write it, the ultimate metaprogramming. For improved parallelism and thread safety, we should make everything immutable. Additionally, I think we should rewrite C Ruby using a microservice-based architecture. Finally, Web 3.0 is almost upon us. It's time to run Ruby in the web browser. Is this kind of a joke? Or maybe not. One question that comes to mind when thinking about what we want for the future is Ruby fast enough? Do we have situations where making Ruby faster would make things significantly better? What do we mean by faster? Do we mean reducing the runtime, increasing throughput, reducing latency? Let's assume we could make Ruby execute code 10 times faster. Is that realistic? Please don't read into this too much, but here's a comparison that Aragon did recently from the Truffle Ruby team. This particular micro benchmark was 23 times faster. The Truffle Ruby implementation can do some amazing optimizations because it's built on the JVM and a mountain of PhDs. Seeing results like this makes me really excited for the future of Ruby. So now we know that it might be possible. What would making Ruby 10 times faster look like? Here is a 1-minute sample of a hypothetical web application. It spends 10 seconds executing instructions and 50 seconds waiting on database and network I/O. By improving Ruby execution performance 10 times, what took 10 seconds now only takes 1 second. To actually achieve this in real code would be an incredible achievement, but we still spent a lot of time waiting and that hasn't changed. What about if we could make Ruby execution 100 times faster? That's probably impossible. But what took 10 seconds now only takes 100 milliseconds. But the overall latency was not greatly reduced. Without carefully considering what it is we want to improve, measuring, profiling, and testing, it's entirely possible you miss the biggest opportunities. So how do we improve the scalability of Ruby? What are the tools we have to build scalable systems? One of the most important is parallelism. If we can execute multiple units of work at the same time, we can reduce the overall latency and increase throughput. So how do we exploit parallelism? At the hardware level, we can use multiple servers. This is especially relevant for application servers and distributed systems, including databases. We can add servers and remove servers as required, which allows us to respond to changes in workload. Within individual servers, we can execute multiple processes. The server can schedule these efficiently over all available hardware resources, and for the most part, they can run independently of each other. If a process fails for some reason, it can be isolated and restarted. This gives them some fault tolerance. Within a single process, we have multiple threads running independently. Sometimes these threads need to access shared resources, causing contention, or even deadlocks. The operating system can schedule these threads across all hardware resources, just like processes. Another important tool is concurrency. By interleaving jobs on a single thread, we can exploit concurrency. Cooperatively scheduling work minimizes expensive context switching and avoids non-determinism. Here we have a thread interacting with a slow I/O device. There are times when it is waiting for a response. By interleaving another job, we can improve the hardware utilization. Given a process that contains threads, we can break it down further. Each thread can contain one or more fibers, each representing a sequential task. These fibers are cooperatively scheduled. When a fiber executes a blocking operation, it yields control to some other task. This can be a big improvement over threads alone because the fiber context switch is much cheaper than a thread context switch, and work can be scheduled more efficiently. So, are threads good enough? Matt says he regrets adding threads. But why is that? Threads can block. If a thread performs an I/O operation, we need to switch to another thread. If all our threads are waiting for I/O, we may need to allocate more threads to handle new requests. Ideally, we would create one thread per request, but is that possible? This benchmark looks at the default maximum number of threads versus the maximum number of fibers. Actually, I gave up after 1 million fibers, so it could create more. But the point is, fibers are much more plentiful than threads by several orders of magnitude. This doesn't prevent you from tuning the operating system parameters, but I don't think anyone is going to recommend you try and create 1 million threads, except as an experiment. Threads are expensive. Most implementations use system calls to create threads, and the operating system must manage scheduling and context switching. Fibers still need to have stacks allocated using virtual memory, but that only needs to happen once and can be easily reused. Therefore, fibers can be created without any system calls, and scheduling is done in user space. So they are very lightweight in comparison to threads. This micro benchmark shows the number of threads and fibers we can use per second. Depending on your perspective, you may see that threads are not so bad, or you may decide that fibers are better. Unfortunately, this is not the whole picture. Threads are not truly parallel in C Ruby. Unfortunately, the Global Virtual Machine Lock, or GVL, ensures that only one thread can execute Ruby code at a time. Because of that, we see a significant reduction in performance when comparing 8 processes with 8 threads. In theory, it should be similar, but unfortunately the GVL adds significant contention, causing a 70% reduction in throughput. Threads are also very tricky. I'm going to quote some points from The Problem with Threads by Edward A. Lee. Threads discard the most essential and appealing properties of sequential computation. Understandability. Threads, as a model of computation, are wildly non-deterministic, and the job of the programmer becomes one of pruning that non-determinism. The end result is that programs become difficult to understand. Programmers are not only expected to follow the logic of the program, but the combinatorial explosion of states that occurs when threads are used. Predictability can be a far more important property than performance. If programmers cannot predict their code, then the code will not be reliable. When building complex systems using threads, understanding the behavior of any given function and how it interacts with other functions is an almost impossible task. Deterministic ends should be accomplished with deterministic means. Non-determinism should be used judiciously and carefully where needed, and should be explicit in programs. This principle seems obvious, yet it is not accomplished by threads. So what kind of model do we want for Ruby? How do other languages work? Let us consider Node.js. It uses a single process model. Recently they introduced isolated workers, which execute in parallel. It's a nice model in the sense that it can work on almost any platform, but it's also a little bit limited. Within one process, event-driven callbacks are used for concurrency. Sometimes this can lead to callback hell. I think it's something to avoid if at all possible. Go is a language which pioneered Go routines. It is roughly equivalent to the green thread model, where several operating system threads are used to manage hundreds or thousands of tasks within the program. This is normally referred to as the NM threading model. It's good because it avoids the limitations of system threads and maximizes hardware utilization. However, it introduces the complexity of threads as well. Internally, the I/O is non-blocking, but the user code will wait until the operation is completed. Erlang was developed from the ground up with the goals like isolation and durability. Share-nothing processes communicate by channels and use MN threading model. Many Erlang tasks are preemptively scheduled onto a limited number of threads. Because the processes are isolated, there is no chance for one process to corrupt the memory of another. This is very similar to the Guild's proposal. Internally, the I/O is non-blocking, but the user code will wait until the operation is completed. What you might notice is that the best systems have harmony in their design. The language and runtime are built around the concerns of parallelism and concurrency. By doing this, the needs of scalability can be met without a huge effort by the programmer. Whatever model we adopt for Ruby, there are many areas which must be in balance, and it's not an easy problem, especially considering that we don't want to break existing Ruby programs. In order to improve Ruby, we must push our limits and challenge our assumptions. But how do we measure success? 1 million connections! Wah-ha-ha-ha-ha-ha-ha! More specifically, I decided to aim for 1 million WebSockets because it's got practical implications. By pushing the limits, I hope to reveal the areas of Ruby that need improvement and ultimately what is required to move forwards. To support 1 million simultaneous connections, we have already seen the evidence that while useful, processes and threads aren't sufficient. We cannot make 1 million processes nor 1 million threads. We definitely want to avoid state machines and callback hell. So what about fibers? I've been working on this for several years now and have already built some important foundations that we can use for this journey. Firstly, let's look at Async. It is a library for implementing highly concurrent clients and servers for Ruby. Its core abstraction is the asynchronous task, which provides Fibre-based concurrency. Tasks execute synchronously from top to bottom, so no special keywords or changes to program logic is required. Blocking operations yield control back to a reactor, which schedules other tasks until the operation can continue. The core of async is less than 1,000 lines of code with good unit test coverage. Lately, I've been looking into async as one of my projects would really benefit from non-blocking I/O. It's really beautifully designed. Janko Moronic on the general design of async. Async has a growing ecosystem of scalable components, including support for Postgres, Redis, HTTP, and WebSockets. There is also a PR to support the event loop within Ruby on a per-thread basis. This is a good solution to take existing Ruby code to the next level of scalability, with almost no changes required when running in a compatible application server. The PR is very simple, and because of this, the same approach can be easily adapted for JRuby and Truffle Ruby. So, just because I love looking at code, here is a short example of async. The code executes sequentially, and we only introduce non-determinism when we actually want it. So firstly, we need to require async. Then we have an async block. Because it's the top level block, it creates an event loop. We need to instantiate the internet, object-oriented programming. We have a list of terms, and for each one of those terms, we start a new asynchronous block, and we query Google and get a response back. We read the response, and we count how many times that keyword shows up, and then we print it out. Finally, we need to wait for all the tasks to complete, and then we close the internet because we're done with it. If you run this several times, you can see that the order of the output changes because the tasks are working independently of each other. This is non-determinism, introduced by the async method. But within each async block, the code runs sequentially. If you would like to try it out for yourself, there is an online tutorial. I'll also put the link on Twitter later. We also need a compatible application server for hosting the WebSockets. Let's look at Falken. Falken is a pure Ruby web application server built on top of Async. It supports HTTP1, HTTP2 with zero configuration. This gives you a modern localhost development environment that can also be used in production. It uses one Fibre per request for concurrency, and it uses a hybrid multi-process, multi-thread model for parallelism. This is required so it can support both C Ruby and JRuby and Truffle Ruby. They all have different internal models. Is it scalable? Well, like anything, it depends on how you use it. For blocking database queries, it can scale very well. In this benchmark, Puma was not able to peg the CPU, but Falken scaled up to all CPU cores were fully utilized. We benchmarked different concurrency levels and looked at how the performance changed. Once Puma reached the limits of its thread pool, which is 16 by default, it couldn't handle any more requests. But Falken was able to keep on making fibers until it hit the limit of the database server. Async is the right model for web applications. Web applications are almost always I/O bound. The Ruby web ecosystem is really lacking in scalability, e.g. WebSockets on Puma. Async unlocks the next tier of scalability in the most Ruby-like way possible. Brian Powell on migrating from Puma to Falken. Does it work with Rails? Yes, it's Rack compatible. There is an online tutorial for Falken as well. It just walks you through the basic setup instructions and how to get a website running. So, are we ready to start the journey? The first 10,000 connections is a good memory for me. When I first wrote Async and Async I/O, C10K seemed like a difficult goal. For those who don't know, C10K means making 10,000 simultaneous connections. And for a long time, it was a goal which reached into the heart of the operating system, the network stack, and the user code, pushing them all to their limits. These days, though, it's C10M. That means 10 million simultaneous connections. That's what kernel developers are thinking about. The very first pain point you will encounter is operating system limits, which are designed to protect your system from rogue software which would otherwise consume resources. These limits and the way to control them vary from platform to platform, but the main one we need to increase is the maximum number of open files, which limits how many TCP connections you can make, and the maximum number of virtual memory maps, which controls how many fibers we can create, each fiber needing its own stack and guard page, which take up entries in the page table. It was also around this time I started looking into the Fibre context switch, which is implemented using the coroutine transfer function. Originally, there were many different implementations in C Ruby, with different interfaces and different performance characteristics. Windows was particularly special. It's the only implementation which combines creating a fiber with allocating a stack. Every other implementation allows us to manage the stack allocations separately. I had a strong desire to normalize this, so I introduced standardized assembly implementations for the core coroutine transfer function. I was then able to standardize the way virtual memory was used for allocating stacks on both Windows and Unix. We still retain many parts of the original implementation, but on all platforms where performance matters, we have assembly implementations. Let's take a look at how it works. Firstly, when you create a fiber in Ruby, we must initialize the stack the fiber is going to use. That function is called coroutine initialize. It takes a context which stores all the information about a coroutine. The start function is a pointer to the code we're going to execute, an area for the stack, and the size that was allocated for the stack. We set up the context with the stack pointer. Then we put null at the top of the stack that prevents the coroutine from returning into no man's land. Then we put the address of the start function on the stack. Finally, we need to copy the number of non-volatile registers into the stack, and they just start off as all 0. The coroutine transfer function is used to context switch from the current stack to the specified stack. By nature, it's symmetrical, and I found this aspect of it very beautiful. Let's step through the AMD 64 implementation and see how it works. First, we need to save the caller state. This is the fiber that is calling the transfer function. We need to push the non-volatile registers onto the stack. Then we need to save the caller stack into the from context. Once we've done this, we're ready to do the transfer. We copy the stack pointer from the to context into the stack pointer register, and it points to the new stack. Then we pop the non-volatile registers off the stack. We prepare the return value of the function as the first argument of the from context. And finally, we call return, which pops the address of the stack, in this case start, and jumps to it. Just for fun, I want to share with you some of the other implementations. Here is a 32-bit x86 implementation. It is very similar, but it has less registers to preserve. Here is the ARM32 implementation. Actually, we have some issues with this, and it's not enabled yet. However, something which I found remarkable about this implementation is that there is no return statement. When we push the non-volatile registers onto the stack, we save the link register, which is the return address. The final statement pops the values off the stack and back into the program counter, and by doing so, it has the same effect as a return statement. Here is the ARM64 implementation. They really seem to embrace risk. So even though it's not that different, the code is much more bulky. Windows, being Windows, decided to invent their own ABI. So the Win32 implementation is a bit different from the previous x86 implementation. It needs to correctly manage the thread information block in the FS register. If you don't do this, it will crash. The Win64 implementation is also totally different from the standard AMD 64 ABI. They just had to do their own thing every single time. One notable point is that 160 bytes of floating point registers must be saved to the stack. It's particularly tricky because the floating point registers can only write to aligned memory, which is why the coroutine trampoline is needed. It's actually used to bounce into the coroutine start function with the correct stack alignment. That one line took me days to figure out. Across all the different implementations, the performance improvements were great and translated into real-world performance gains of about 5% in my tests at the time. Not only was it faster, the code was simpler as well. Getting past 100,000 connections was where things started to get more messy. There is a certain point when testing on localhost that the operating system won't be able to make any more connections. TCP connections in your network stack are uniquely identified by a source address, a source port, a target address, and a target port. You run into this limit because the port number is only 16 bits wide, and there aren't enough ports to uniquely identify 100,000 connections in the network stack, if everything else stays the same. So if each client can only make 25,000 connections, we need several of them to pass 100,000 connections, each bound to a different local address, 1271, 1272, 1273, and so on. You don't tend to encounter this issue in the real world because every client would come from a different source address, but in a test environment, it can be a big problem. This could also potentially be an issue if you have a proxy server. In any case, this solution was short-lived because a better solution became apparent later. It was also at this point I started to experience my first garbage collection performance issues. We can see here that the garbage collection time is roughly proportional to the number of connections. Every 100,000 connections increases the garbage collection duration by about 1 second. By the way, I made this screenshot from an aeroplane while connected to my server in the garage in New Zealand using SSH. That was really exciting for me. My initial investigation focused on how many and what kind of objects were being allocated per connection. I found that around 200 to 300 objects were being retained, which felt excessive. I carefully went through the code to investigate. I found out that C-Ruby cannot release objects on stack frames even if they are never used again because of the design of the language. In code like the WebSocket connection handler, the request and response objects are retained indefinitely. After we negotiate the connection, the request and response objects are no longer needed. When yielding the connection, all the objects in the stack frame will be retained until the stack frame returns. The easiest way to avoid this is to set any unneeded locals to nil so that they can be freed. That might not seem like a big deal, but it can make a big impact. With some careful refactoring, it was possible to reduce the per connection overhead from about 200 allocations to 50 allocations. The estimated total heap space required for 1 million connections was greatly reduced. Sorry. The animation. Oh, there we go. Is it coming? Oh, there we go. This also helped improve garbage collection performance because there were less objects to mark and sweep. It was at this point I started to reevaluate the entire approach I was taking. Getting to 250,000 connections with 25 connections per client would require 10 clients. To get to 1 million connections would require 40 clients. It felt like a very cumbersome solution. I started investigating other options. When I first started implementing Async HTTP2 client and server in 2017, there was no standard for HTTP2 WebSockets. After experimenting with HTTP2, I came to the conclusion that it makes WebSockets irrelevant. HTTP2 has technically superior multiplexed bidirectional streams. The only reason we can't use this is because web browsers don't expose it very well. WebSockets remain the most compatible solution. Somewhat unexpectedly, in late 2018, an RFC was published standardizing how to implement WebSockets over HTTP2. It outlines how to run the WebSocket protocol over a single stream of an HTTP2 connection. As you may know already, HTTP2 can multiplex streams over a single TCP connection. So I implemented it with a stream-to-connection ratio of 100:1, which allows us to achieve 1 million WebSocket connections with only 10,000 TCP connections. Interestingly enough, this didn't change the performance all that much. Each connection still takes up roughly the same amount of resources within Ruby. If anything, HTTP2 per stream overhead is slightly higher. But the simplified client implementation was great, and I'm very happy about using it. It was also around this time I started to revisit the Fibre implementation. I was concerned that allocating millions of fibers would be a big overhead. Is it possible to allocate them more efficiently? Part of the Fibre allocation code is shared with a thread allocation, and I ended up working on that first. A Ruby thread execution context has two stacks: a machine stack allocated by the system and a virtual machine stack allocated on the heap. The machine stack is used by compiled C code, and the VM stack is used by interpreted Ruby code. When you print a Ruby backtrace, it iterates over the activation frames in the VM stack to see what methods were invoked, print their names, and so on. When I was pushing this to its limits, I found some strange situations where Ruby could create a thread, but it couldn't allocate the VM stack because the system was out of memory. I investigated and discovered that we could avoid this case by increasing the size of the machine stack and using it for part of the VM stack. This approach simplified the code and avoided the odd failure case. It also improved performance a bit, reducing thread allocation cost by about half. Simplifying thread creation paved the way for improved Fibre allocation. My goal was to make asynchronous tasks as lightweight as possible, to encourage their use. In order to do this, creating and reusing fibers should be as fast as possible. Like the original implementation of Thread, the Fibre execution context used a heap allocation for the VM stack, which added unnecessary overhead and failure cases. There was a fixed size cache of 10 machine stacks, which could be reused, but on a server handling thousands or millions of requests per second, it was simply too small. Building on the previously improved Fibre implementation, I introduced a new layer to create and reuse stacks efficiently. The Fibre pool serves two important purposes: the bulk creation of stacks and tracking vacant stacks which can be reused. The bulk allocation reduces the number of system calls required to allocate many stacks, up to 1,024 stacks at a time in the current implementation. And when we are finished using a stack, it gets added to the vacancy list, which is stored in line with otherwise unused memory, allowing for efficient stack reuse. The improvement was very impressive, between 7 and 11 times on platforms we care the most about. And it makes fibers very inexpensive. Sorry, I just slipped that one in there. It makes fibers very inexpensive to use and reuse. It was also at this point I started running into the limit of my test server's memory, which is 64 gigabytes. I thought, oh no, I need to provision something on AWS with 128 gigabytes of memory to run this test. Then I started looking at object allocations again and noticed that for 500,000 connections, there were 1 million tasks being created. When I originally added partial hijack support to the HTTP2 implementation, I followed the path of least resistance and added a separate task wrapping the user code. In this case, the WebSocket connection. It communicates using a queue. It was fine and it worked well, but it doubles the number of tasks which are required, and that essentially ended up doubling the amount of memory required. By carefully exposing the stream I/O to the client code, which was invoking the partial hijack, it was possible to reduce this to 1 task per connection. While this might not seem like much, the total memory usage, which was around 48 gigabytes for 500,000 connections, dropped by almost exactly half to around 24 gigabytes for 500,000 connections. That is 16 kilobytes per connection. This was the last step required to run this experiment, both client and server within 64 gigabytes of memory. So it's at this point, I'd like to invite Mats up on stage to make the 1 millionth connection. Mats here. You can come up. Hold on, I just mirror my display. I did not expect that. Oh, no, it's over there. Okay, excellent. So this is the code that is going to run when we hit 1 million connections. It's going to print out a nice statement. Here is it running in my server in the garage in New Zealand. The server is currently using about 22 gigabytes of memory, and there are 4 what I call multi-clients, and they're all connected. They use about 5 gigabytes each. Anyway, let's see if the whole thing collapses. There you go. Press enter. That one. There's like a timer. If you feel that. 6, 5, 4, 3, 2, 1. Oh, well, there we go, live demonstrations. But that is 1 million connections. Oh, there we go. Thank you very much. I'm honored to have you as part of that journey, by the way. There we go. So, what are the next steps? Improvements to garbage collection, green process models, guilds, exposing non-blocking hooks. There are many directions. It depends on you. The community, please try it out. Give me feedback and tell me what it's like, if it works, if it makes you happy. And businesses, please consider sponsoring this work. We have a funding model for sponsorship, so if you have an interest in this kind of thing and you want to support me to make Ruby better, feel free to get in touch. Thank you very much.
Thank you. Thank you and congratulations. Do we have any questions? Do we have any questions? Please raise your hands. Don't be shy. No question at all.
I'm happy with that.
You okay?
Yeah.
Is there anything that you want to say?
No, I'm good.
You're good?
Yeah, I'm good.
Ready for the party tonight?
Yeah, I'm ready for the party.
Okay, what time's the party? 6:30 is the party.
I think it's 6:30.
Yes, 6:30 on the 8th floor.
I think it's 4.
Yes.
Downstairs.
Downstairs.
Excellent.
Yeah, great. Well, thank you very much.